Today I will show you a modeling and simulation workflow with an antibiotic in order to find the dosing regimen that optimizes the bacterial killing. The primary measure of antibiotic activity is the minimum inhibitory concentration, MIC. The MIC is the lowest concentration of an antibiotic that completely inhibits the growth of a bacteria in vitro. It varies, of course, from species to species, but also from strain to strain. To determine the MIC of a strain in an infected person, a susceptibility testing can be done in vitro using a sample from an infected site. However, the bacteria needs to be killed in vivo, where the drug concentration at the site of action is changing over time. The time course of drug concentration is usually summarized by the PK parameters, such as Cmax or AUC. Combining the PK parameters with the MIC, 3 PK/PD parameters have proven useful to predict the effect of an antibiotic in vivo. First, the maximal concentration Cmax divided by the MIC, the time above MIC, which is the time during which the drug concentration is higher than the MIC, and finally the AUC between 0 and 24 hours divided by the MIC. Which PK/PD parameter to use depends on the type of the drug and its mechanism of action. The time above MIC works well for drugs showing a concentration-independent, time-dependent effect. That's the case for beta-lactams antibiotics and the macrolides, for instance. For this type of drugs, clinical studies have determined a minimal effective time, which is the duration during which the antibiotic concentration must be above the MIC in order to achieve cure. On the opposite, some antibiotics have a clear concentration-dependent bacterial killing effect. Then, the best PK/PD parameter is the Cmax divided by MIC. Aminoglycoside and fluoroquinolone belongs to this group. For this group, a Cmax over MIC ratio of at least 10 within the first 24 hours of treatment has been shown to result in a 90% cure. Choosing a dosing regimen in accordance with the relevant PK/PD parameter is thus important to optimize the effect and also for minimizing the risk of resistance. In this case study, we will work on a PK dataset for erythromycin, which is a macrolide. I will show you how to model the data step by step, how to calculate the PK/PD parameters, and how to perform simulations to optimize the dosing regimen. In this dataset, 19 healthy individuals have received a 500 mg oral dose of erythromycin stearate. The plasma concentration was measured at time 0.5, 1, 1.5, 2, 4, 6, and 8 hours after the dose. To start developing a model, I have opened Monolix, start a new project, and browse to select my dataset, which is a CSV file. The columns ID, time, DV, and amount are automatically recognized and tagged as ID, time, observations, and amount. I can accept the dataset and have a look at it using the data viewer. The data looks pretty clean, going up and down. If I check on the log scale for the y-axis, I can see that a one compartment model will probably be enough because I see only a single slope during the elimination phase. So I will close the data viewer, click Next, and select a model from the library, PK. I now have an oral administration. I will select no delay at first. Let's try a first order absorption with a one compartment model and a linear elimination. I will take the model parameterized with KA/VK. And this brings me to the next tab where I can choose the initial values, and I can use the auto init button to automatically find good initial values. I set them as initial values, and in the statistical part of the model, I will keep the default choices with a combined error model and log normal distributions for all parameters. I will select Alt Task, save my run. as run number 1, for instance, and run. In the diagnostic plots and in the individual fits, I can see that it seems that for all individuals that I can display all on a single page, I kind of miss the Cmax for most of them. If I look in the observations versus predictions on log-log scale, I can see this smear, and if I hover over the dots, I can see that they all correspond to the first time point at 0.5. If I go back to the individual fits and zoom on the x-axis on the small times for all individuals, I can see that I actually miss a t-lag. The concentration is going up too early in the prediction. So I will change my model and add a t-lag. So I go back to the structural model, go back to the library, and this time select a model with t-lag, still using the parameterization with the elimination rate. In the initial estimates, t-lag is for the moment too large. I will reduce it to 0.3, for instance, that is below the first observation at 0.5. I set those as initial values, save under a new run. Let's call it number 2, and run again. This time the individual fits look much better with the Cmax properly captured. And if I look at the observations versus predictions on log-log scale, it looks also much better and the smear have disappeared. I can also browse through the other diagnostic plots. These are the residuals. Here it's the distribution of the individual parameters. What I can see is that the distribution for the volume seems to be bimodal with 2 different bumps if I look at the blue histogram. This bimodal distribution could maybe be explained by a covariate such as sex or weight, but as I don't have this information, there is not much I can do. The only option would be to add a latent covariate on the volume. This works nicely, but it would bring us too far for this case study video, so I will leave it like this. That's a distribution of the standardized random effect. I also would like to generate the VPC, so I will go back here to the plots and add the visual predictive check, and it looks good. So this was the diagnostic plots. I will also have a look at the results. So here I have the estimated parameters together with the relative standard errors. I see that they are reasonable, except maybe for omega t-lag, which is a bit high. If I look at the tests, I can see no red p-values, meaning that I have no correlation to add in the model. So I can consider this as my final PK model. I have a 1-compartment model with first-order absorption and a t-lag, and a combined error model with a constant and a proportional term. I now would like to use this model to calculate the PK/PD parameters and check their value for different dosing regimens. I will do this using Simulx, our application for simulations, which currently comes as a R package. I have set up an R script to show you the different options. In this R script, the first thing I do is to load the MLXR library, which gives me access to the Simulx function. The Simulx function can very efficiently reuse the information of the Monolix run if I pass as a project argument the path to the Monolix project. This is my r02.mlxtrend file I have generated just before. To calculate the PK/PD parameters, I can either output the concentration over time and post-process these values, or I can implement them directly in the model. I will show you both options, and I will first focus on the time above MIC, which is a relevant PK/PD parameter for erythromycin. To calculate it, I will write a small piece of code where I define the variable t above MIC, which has initial value of 0, and a time derivative called x that I have defined just above using an if-else statement. If the drug concentration called Cc in the model is above the MIC, then x is equals to 1, otherwise it is equal to 0. A time derivative equals to 1 when it gets integrated becomes a time. So t above MIC will record the time during which the concentration of the drug is larger than the MIC. The MIC value needs to be hard-coded in this piece of code, so I have written above MIC equals 0.5 microgram per ml. That's the MIC that has been measured for the strain I'm interested in. In order to add these lines of code into the model, I define them in an object list with a field formula. This object is called lines to add, and I give this object as an input argument add line to the Simulx call. With this procedure, these lines of code will be squeezed in at the end of the structural model when performing the simulation. I would like to calculate the time above MIC for the individuals of the dataset used for the model development. To do so, I will add an argument parameter equals mode. This will prompt Simulx to use the EBEs, so the most probable parameter values estimated by Monolix, to perform the simulation. And finally, I will define the output. I have two different objects. The first is to output the time above MIC at the end of the simulation, so at time 24, for instance. And the other one is to output the concentration Cc on a regular time grid from time 0 to time 24 hours. Once I have simulated the values, I can use ggplot to plot the result. I can zoom on the plot. So these are the predicted concentrations for the individuals of my original dataset, and I have added a black line at the MIC value, so at 0.5 microgram per ml. The value of the time spent above the MIC is stored in another field of my res output, and I can print it to the console, for instance. And here I see for each individual of the dataset the time in hours during which the concentration was above the MIC. Actually, for erythromycin, the target time above MIC cannot be achieved with a single dose. Multiple doses are required, and it has been shown that maximum killing is reached when the drug concentration is above the MIC at least 50% of the time. So let's modify a bit our piece of code to calculate the percentage of time spent above the MIC. To do so, I add a new variable percent time above MIC that is just the time spent above the MIC divided by the total time times 100. If I now want to investigate several dosing regimens, I can define different type of administrations. Here I will try two different strengths of tablets, 250 and 500. That's the two that are available commercially. And two different interdose intervals, either 6 hours or 8 hours. To test these four different treatment options, I will define four different groups, which will each have 100 individuals and one of the four treatments. To define the simulation, I will proceed as before. I have the path to my Monolix project from which I will reuse the model and the population parameters. I will add those additional lines to the model, ask for the same outputs as before, but redefined the number of individuals and the treatment by giving the list of these 4 different groups. In each group, the individual parameters will be sampled from the population distribution. To plot the results, I will use the function percentile MLX, which is part of the MLXR package that enables me to plot a prediction interval. And these are the simulations I get for the 4 different dosing regimens. I now would like for each group to count the percentage of individuals which indeed spend more than 50% of the time above the MIC. To do so, I will use the function aggregate, which is a basic R function, on the percent time above MIC. For each group, I will count all the individuals which have a percent time above MIC larger than 50%, divide by the total number of individuals, and multiply by 100. This gives me the percentage of individuals which spend more than 50% of the time above the MIC. I can then print this value into the console, and I see that for the 250 milligram every 8 hours, only 11% of the individuals are in the target. With either 250 milligram every 6 hours or 500 milligram every 8 hours, I have around 70% of the individuals in the target. And if I go up to 500 milligrams every 6 hours, then I have almost everybody spending more than 50% of the time above the MIC. So this was an example about how to calculate the time above MIC. I will now show you how to implement the 2 other PK/PD parameters. I have set up examples below. For the AUC 0 to 24 divided by the MIC, I will also use the add lines. The AUC is calculated as the integral of the concentration, and then the AUC over the MIC is simply the AUC divided by the MIC, which is still hard-coded. If I now output the AUC over MIC variable at time 24, I will get the AUC from time 0 to time 24 divided by the MIC. If you need a time interval AUC, please refer to the feature of the week number 38 or to the online Monolix frequently asked question section. So this is how to proceed for the AUC divided by MIC PK/PD parameter. Now let's see how to proceed with the Cmax. With the Cmax, it's less easy to use the add lines because the Cmax can be calculated directly in the model file only if the model is written as ODEs, which is quite limiting for PK models. Please refer to the previous feature of the week video if you want to learn more about this. So alternatively, in this case study, I will show you how to post-process the output concentration to calculate the Cmax over MIC. So the first step is to run the simulation and to output the concentration on a fine grid. This is what I do here with the argument output, where as output CC, I can then post-process the predicted concentration using again the aggregate function, and this time I will, for each individual, calculate the maximum of all CC values for each individual and divide by the MIC, which is coded here just above. If I run this small piece of code, I will get again the plot as before, and in the console the Cmax over MIC for each individual. So we have seen how to calculate the 3 typical PK/PD parameters, either on the original individuals and treatment or on new individuals and new treatments. To finish, note that the AUC divided by MIC or the time above MIC can also be added directly in the structural model file in Monolix, and output using the table statement to get the values for the design and individuals present in the original dataset. However, this has the disadvantage to slow down the estimation because an ODE integration is calculated in addition to the analytical solution. Have a nice week!